going to start you guys off with the question, and I think we kind of have the answer, but kind of what was your first motivation to reuse data? Well, you talked a bit about this, like you don't want people to redo an experiment that's already been done, right? You want them to be able to reutilize that. But for you personally in the lab, like what got you started down this path of setting up this this is a huge amount of work that you've gone through to build out these systems. What do you think incentivized you to move in this direction in your career? And Jason, you're after him.
I think what really pushed me in this data reuse direction is some of the consortium projects that have been generating like an astronomical amount of genomic data. And just seeing how many PhDs and papers have been produced as a result of this data just makes me think that, we're barely scratching the surface of the data that we're already producing.
Data reuse is critical, and a lot of the times where it comes to me is actually trying to find data sets that we can teach with, or that others can teach with, that show useful things, and also hopefully get students, learners of all levels in front of data that actually resembles what they're going to have to tackle in the lab. So you want to give them a realistic data set. And one of the difficult things of doing that is, yes, there's something along the order of, I forget the number, but it's in the quadrillions of data of nucleotides available in the sequence read archive. And the level of metadata, which Will sort of described to it, description of those data is often very sparse and uninformative. And so knowing what you can reuse to teach and what was the original data used for, and what else might be able to be extracted from that data set is often unclear. And that's a big thing, because there's very big pushes to make data open and available and accessible. But if you don't give people parallel instructions or enough metadata so they know what they're reusing, you're losing certainly somewhere some of that value.
Yeah.
In terms of personally, I like being at the beginning of somebody's journey, getting into learning with some of these computational tools, because I've seen how poorly it can go. I've seen people teach some of these topics in such a way that I would say, if I was in the classroom, I would never do, because you've just shown me it's super hard or it's unintelligible. You're teaching with so much jargon and lingo that I would just like, oh, okay, this doesn't make sense, or it's not for me. So I really like being able to work with people who are learning these things for the first time, so that we can slowly build up their ability to understand exactly what they're doing and find their autonomy and find their interest in the topic and the subject, and guide them through the parts that might seem difficult or hostile at first, and realize actually that once you sort of swim in the water, even though it's cold at first, it'll become comfortable once you become adapted to it, and you just got to survive that initial shock.
Our group just published 2 papers. One is in yeast and one is in human, basically surveying protein binding in the yeast genome and the human genome. Each paper generated 1,200 unique genomic data sets across about 10 terabytes apiece for just 2 papers. And essentially every paper that we'll be producing from here on out, not quite that large, but are certainly in the multi-terabyte range with hundreds and hundreds of unique data sets. And this ranges the raw sequencing data, process data, so the aligned BAM files, peak files, downstream coordinate files that may be turned into heat maps or composite plots or bar charts, the actual raw data that makes figures. And we also have the thing that tends to be neglected the most, much to every single PI's horror, which is the sample meta information. So traditionally this is a lab notebook, right? And some of these projects can span many years, multiple graduate students, depending on the scale of the larger project. And now you have a stack of lab notebooks that you have to go through when it's time to publish a paper. And God help you to try to get out, the exact lot number of the antibody used for an experiment 6 years ago, because it's going to take you a while, and the odds are it wasn't written down in the first place. And then the final problem, which is kind of the completing the circle here, which is that data dissemination. So even if you have all of this data, how do you get it back out to the community so that they can see it, reuse it, and feed back into the system of more biological discovery? And kind of the thematic idea that kind of underlies everything that we've been building in the past few years is this idea of, the main themes here are rigor, reproducibility, and dissemination. And if you don't have that platform, none of this is relevant because it's never going to be reproducible, and any discovery that's not reproducible is essentially not a discovery. So we, many years ago, we sat down, me and several other PIs that I work with, and tried to figure out how can we start getting a handle on this. And we broke it out into kind of two very broad ideas, which is, well, there's bioinformatic reproducibility and there's biochemical reproducibility. So I'm relatively new to Cornell. I've only been here for about a year and a half now. I came from Penn State, and one of the things that Penn State, is somewhat famous for in the bioinformatics space is the original creation of the Galaxy platform, which is an attempt that has now really blown up with over 100,000 active users around the world to solve this problem of bioinformatic reproducibility. So Galaxy it's a web-based platform designed to have 100% reproducibility of every analysis that ever goes through it. And it's a web platform. There's not only a public usage website that anyone can go to. There's a hosted one here in the US, there's one in the EU, there's one in Australia, but there's also systems for spinning up your own personal Galaxy if you want to do a custom flavor in terms of what kind of analysis you're interested in. And Galaxy is designed to track every single aspect of bioinformatics in these kind of workflow-esque patterns here. So, if you were to upload a FASTQ file, you can plug it into a QC analysis, you can plug it into a BWA for mapping, you can plug that into Picard for QC of the mapping data. And not only will Galaxy run this, as if it was a GUI version of a shell script, it will actually in perpetuity track all the meta information associated with this analysis forever, and guarantee that if 10 years from now you were to rerun this analysis, you would get byte for byte the identical output back out that you did, back in 2010, repeated now in 2022. So we adopted this system, and we were actually really happy with the ability to kind of recapitulate all the analyses that we're doing kind of in bulk here. And now we have this meta information tracking system that was allowing us to keep track of all the different analyses we're doing for the thousands of data sets that we have been generating over the years. But the problem we encountered here was that while we were now able to track all of our bioinformatics, this didn't necessarily help anything on the biochemistry side of things, because we were still tied into this idea of requiring a wet bench lab notebook in terms of, okay, a technician will do this experiment, they'll write it down, they'll submit their samples for sequencing, and now we have the sequence analysis, which is now completely reproducible, but no longer has a direct connection back to the actual experiment that was done. So we ended up building a platform for epigenomic research that we were hoping would, finally close the loop in terms of linking biochemistry to bioinformatics. So it's a custom open source metadata information tracking system. We built this from scratch. It's a Groovy Grails with the MariaDB backend. It's under review. So if you're a reviewer out there, please have mercy on us. And its goal was to link and kind of create a Galaxy-esque interface that did the same thing for bioinformatics and Galaxy that we could hope to reproduce on the biochemical side with Seger. So some of the functionalities it has is an inventory system, so an open source LIMS system that creates a unique QR code for every single reagent that you would ever have on the bench that a technician could just kind of scan with their phone, and it would do remote post requests to the Seger database to kind of in real time update the experiment as it went, so that Seger could now in some part take place of the lab notebook. In addition to that, it also had native support for integration with both Galaxy and the next software platform I'll show you that allows a user to, at the end of the day, they did their experiment, they submitted their sample for sequencing, and now in the exact same website that is now hosting all of their sample meta information, they'll now have all the downstream bioinformatic analysis associated with it. So, de novo motif searching for like immunoprecipitation experiments, composite plots of tag distributions relative to that motif, basic sequencing statistic information in terms of how many reads were there, what the mapping percentage was, as well as links to, the strain. This was done in yeast. This was the genetic mutation of this yeast strain. It was grown in YPD. There was heat shock, et cetera, kind of linking from a complete end to end, or, in this cartoon here, we have a circle that represents the conception of the project, the doing of it, the bioinformatics, the biological discovery, the publication, and then kind of, bringing it all the way back to the next experiment you would do. So where we've been going from this since we've, submitted the Pegger system has also been in parallel the building of the stencil, which kind of ties into maybe the thematic aspect here of this panel discussion here, which is about data reuse. So one of the things that we really wanted to do for our graduate students and postdocs in the group here is the ability for them to rapidly reuse the data that we've been doing. So I mentioned, those two papers represented about 2,400 data sets that we generated. We have thousands more, both in projects ongoing and previous publications that we've been doing. And we hate it when people redo the same experiment when it's already existing in our system. So we've been trying to build out ways for them to rapidly reuse that same data and reanalyze that data in new novel ways. And for that, we've architected out our stencil system, which is, again, another open source web platform. This one is React Node.js for that kind of reactive interactive front end with a MongoDB backend. And here's two of the websites that we've since created and published using this system. With the idea that this is, hopefully you guys can see this GIF here. This is the kind of live capabilities that we're looking to expand out as we continue to develop this platform, that essentially the goal is to live stream that data from the Galaxy server, allow users to manipulate it on the fly. And the key here is that between Galaxy, Pegger, and Stencil, we have a complete end-to-end capability in terms of linking this final analysis that a user might do to make this composite plot, to make a biological discovery. We should be able to link it back to the bioinformatics in terms of the exact scripts and parameters used to make the raw data, all the way back to the biochemical assay that was used to generate this data from a sequencing perspective, and all the way go, in theory, to the lot number of tris used in the wash buffer to actually wash the cell pellet that was, the very starting material for this experiment.